Okay. Now, last class we are discussing about the basilar membrane. Okay. So, if you see this picture, this is the basilar membrane which is inside the cochlea. So, the cochlea is full of liquid and basilar membrane is floated there. Okay. So, you can see the basilar membrane divided the cochlea in two parts, one is called upper and lower part. Okay. Now, this is the beginning part and this is the end part of the basilar membrane. So, this is the apex and this is the base. Along the cochlear membrane there is a some, you can say the there is a some kind of nerval arrangement, that is called, if you see there is a we call inner hair cell. So, there is a inner hair cell basilar membrane, there is a this kind of, you can say the nerval sensor. Let us think about the nerval sensor, there is a sensor kind of things in there. So, if I see, if I all along the basilar membrane, and it is responsible, the high frequency sensing nerve are present in here and low frequency are here. Why? Because if you see in speech production side, due to the radiation load, the low frequency signals are high amplitude, frequency are high amplitude compared to the high frequency. So, the acoustics wave, which is speech wave which is coming, that has a high frequency or less amplitude compared to the low frequency sound. Okay. So, the mechanical motion or high frequency mechanical motions are amplitude are less. So, that is why those high frequency sensors are in the beginning and in the apex are the low frequency sensor. Okay. Now, each this kind of sensor acts as an responsible for a particular frequency range. So, I can say this is the basilar membrane, let us this divided with a, this is the sensors, each of the sensor is responsible for particular frequency band. So, let us this perceive 0 to 5 hertz, let us this perceive 5 hertz to this 10 kilohertz, or I can say 2 hertz to 6 hertz. So, there is a overlapping frequency band is perceived by each and every sensor. So, I can see the basilar membrane is nothing but a output of a different filter bank. If I think in engineering model, I can think the human conversion of acoustical signal or you can mechanical signal to the nerval signal is nothing but a sensor or nothing but a tank circuits, or which is a particular filter or tank circuits, or you can, the sensor is active for a particular band, then it is called tank circuit. So, it is a tank circuit, this is H1 sensor, there will be H2 sensor, there will be H3 sensor. So, H1, H2, H3 is nothing but a band pass filter, I can consider. So, I can say it is nothing but a filter bank analysis by the human basilar membrane. So, whatever the input signal come, it pass through a particular band of filter and ultimately response of the each band is the neuron signal, and that goes to the central brain system, so that it can process for human cognition. Okay. So, how it is convert mechanism is called inner hair cell. There is a lot like the inner hair cell, each of that sensor, there is a 10 to I think 10 nerve fiber each of the different diameter. One inner hair cell consists of 10 fiber, auditory nerve fiber. So, that convert that things. Okay. So, now come to that, we know that how human being perceive the sound, how human basilar membrane convert that mechanical motion to nerval motion. Now, think about in engineering model, we said, so basilar membrane responds maximally to different input frequency tuning occur at basilar membrane. So, I can say that each of the tank circuit is responsible for a particular frequency band, which is a constant Q filter. Okay. So, I can say this is particular frequency band, this is also responsible is particular frequency band. Then I want to know, is this band are linear or is this band are non-linear. So, bandwidth of the each of the particular filter, is it linear overlapping or non-linear overlapping? How do you define that? How do you know that things, whether it is a non-linear and linear? So, we can do some experiment, later I will come. So, these bands are called, you can say that Bach scale. So, I will come later on that what is Bach scale. So, physiologically I can say human perception or human the frequency which is heard by the human being or sound which is sensed by a human being is done on the basiliar membrane, where it is as a different frequency tank circuit. Okay. And bandwidth of nonlinear. Okay. Then we will come later on that what is how do you define this nonlinear scale. Then how do you perceive the frequency? We said each one is the particular band. If it is band, then how do you perceive the frequency? Because this is nothing but if it is this is a particular this is nerve fiber, this is nerve fiber. If I say this is the for high frequency and this is for low frequency, then or this, suppose I said I have a frequency response 20 hertz to 20 kilohertz. There is a 100 tank circuit. I know the bandwidth of each and tank circuit. Now, suppose I want to perceive some. So, is it is 20 hertz, it is 30 hertz like that way or nonlinear way, and whether this fiber, how this fiber is responsible particular frequency, that I want to know. So, there is a two theory, one is called temporal frequency, which is called temporal theory, and another is called place theory. Okay. So, this first theory is that the basic of the temporal theory of the pitch perception is timing of neural firing, which occur in response to vibration of the basiliar membrane. Timing of the neural firing is perceived as a frequency. So, periodic stimulation of membrane match frequency of sound, once electrical impulse at every peak. Next one is called place theory. Wave move down basiliar membrane, stimulation increases peak and peak quickly taper. Location of the peak, if you see, if the stimulation I have stimulated the cochlear and that increase the peak motion is. So, I can say this is my basiliar membrane, this is so if I wave is mechanical wave is stimulated, then this will be look like this, the wave will moving like this along the basiliar membrane in a wave. So, stimulus increases the peak and quickly taper. If I say this portion is increase and taper, increase and taper. So, increase and taper and increase, this kind of motion will be happen. So, location of the peak depends on frequency of sound, lower frequency being further away. So, if the peak is occur in here, location of the peak if occur in here, then it perceive the frequency. So, there is a one is called timing, another is called location of the peak. So, that is why local place theory, another is called frequency or temporal theory, frequency theory. Okay. Now, human being perceive the sound. Okay. So, I can say that human perception of an input sound has two parts. One is the perception of the frequency, another is the perception of the amplitude. So, if I produce a, you can say the let us 500 hertz acoustic signal, it has a frequency, it has an amplitude. So, human being perceive frequency and also perceive as well as perceive the amplitude of the particular frequency. So, two perception things is there. Now, I have to know how accurate we are in perception of amplitude and frequency. What do you mean by accuracy? You can say, think about the resolution. Okay. So, suppose I have a straight line and I want to measure the straight line in some small scale, or I say there is a line which is like this. If I want to measure in a scale, small scale, so I put the scale along this line. Now, if my scale is larger, then I put the scale here and again I put the scale here. Now, if you see, if I approximate it long section, then I may lose some error or I may introduce some error. So, that means how accurately I can perceive the sound. So, a human being perceive every hertz of the sound? If it is possible that the human being will perceive 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz, 6 hertz, 7 hertz and like that way, or for a particular frequency in a band. Similarly, if I increase the intensity, are we able to linearly perceive the intensity increase or in which scale? Whether I am able to differentiate between the 2 dB and 2.5 dB or 2.12 dB or not. So, that is the resolving power of the human being I have to know. Okay. How good an estimation of the fundamental frequency? So, in the frequency domain and intensity domain, there is some parameter. Fundamental frequency, the resolving power is 0.3 to 0.5%. So, if I say my F0 is 200 hertz and somebody's F0 is less 201 hertz, whether can I am able to differentiate between this 200 hertz and 201 hertz? It said it is 0.3 to 0.5%. That means, if the difference is lie between this range, we cannot differentiate the two frequency. So, we cannot separate them. So, let us 0.3, let us 0.3. So, 0.3% means 0.3 divided by 100 into 200, let us. So, 0.6. Okay. So, if it is let us if it is for the 300 hertz, then 0.9. So, I can say approximately 201 hertz frequency and 200 hertz frequency I cannot differentiate. If it is 1 kilohertz, then 0.3 by 100 into 1 k, it is nothing but a 3 hertz. So, if I say the perception of the frequency is different in different frequency range. So, it is not a linear scale, it is a non-linear perception. So, how do you perceive? If it is a high frequency, the difference, the perception will be more rough. I can say the bandwidth will be, perception bandwidth will be larger. Okay. So, I can say that initially for the low frequency, my resolving power is very high, but at high frequency, resolving power is very low. So, that means at high frequency, I cannot separate the two, let us say 1 kilohertz and 1.003 hertz, that I cannot, kilohertz, I cannot separate. But at low frequency, almost 1 hertz difference I can understand. So, low frequency level human perception resolution power is much more, high frequency level we do not have that much of resolution power. Okay. So, in high frequency accuracy, so suppose suppose I want to copy an instrument. So, I can say high frequency details informations are not that much of required, because human being cannot perceive the high frequency in a high resolution. Okay. Fundamental, then the formant frequency, to know the formant frequency is nothing but a formant position in the speech. So, first formant around 500 hertz. Okay. So, if it is uniform to you 500 hertz, so almost 500, around 500 hertz will be the first formant. So, I can say 3 to 5%. So, if it is 500 hertz, then 3 divided by 100 into 500. So, almost 15 hertz error in formant human being cannot differentiate. So, suppose I extract a formant frequency of a particular vowel, let us 450 hertz. If it is differ by 10 hertz instead of 450, if it is 460 hertz, then also human being cannot distinguish the difference, because we do not have resolving power of this formant position. Then formant bandwidth 20 to 40% error. So, suppose let us has a first formant bandwidth, let us 65 hertz. Okay. Even if instead of 65 if it is 20% error. So, 20 to 40% variation we cannot distinguish. So, let us 30% variation we cannot distinguish. So, 30 divided by 100 into 65, 18 hertz difference. So, instead of 65, even if it is 65 plus 18 hertz, then also we cannot see any difference. That is called just noticeable difference, JND. So, due to the limitation of human perception, we cannot distinguish if the range is within this limit. Intensity 1.5 dB overall. If it is 50 dB and if it is let us 51.5 dB, no difference. For the same frequency, if the two 50 dB and 51.5 dB, we cannot perceive the differences. Okay. Now, I come to the physical dimension of the sound and physiological, or you can say the psychological perceptual dimension of the sound. So, that is obvious, you know that height of the amplitude, frequency, wavelength and their property, you know that. Now, I call auditory perception. So, auditory perception is branch of psychophysics, you know that. So, perception and physiology, physical property of stimuli. So, physical dimension, as we have said, is the measurable, but perceptual dimension is the mental exercise, or you can say physiological output. If I excited by a physical stimulus, what kind of output I observe, based on that characteristics I can measure the perceptual dimension parameter. Now, if it is sound, I have not detailed discuss about the human visual auditory system, visual psychophysics, auditory psychophysics. Pitch, loudness, timbre are called perceptual dimension of the speech, or you can say the sound wave or sound perception of the human being. Pitch, loudness, timbre. Physical properties, fundamental frequency, intensity, spectrum envelope or amplitude envelope, you can say. So, what is this? If it is a pitch, sometimes you see that many of you maybe practices music. You say that somebody, some guru said that okay, you set the harmonium at flat B scale, because your pitch will be around let us 200 hertz, so flat B, or 180 hertz flat B. So, that is nothing but an average pitch, we say average pitch, but pitch is a perceptual parameter. So, 180 hertz is nothing but a fundamental frequency, average fundamental frequency of that singer, not the pitch. So, we sometimes we say the pitch. Example is that suppose I play a tanpura and a harmonium and a say guitar, let us sa, and with the same frequency, harmonium sa has 200 hertz, tanpura sa also has a 200 hertz, also let us the tanpura, harmonium and guitar 200 hertz. All instruments are producing sa of the same frequency sa, but even if I closing my eyes, I can identify this sound is coming from harmonium, this is for tanpura, this is for let us guitar. So, how do you find out? If all pitch are same, if I say the fundamental frequency is the pitch. So, pitch is a perceptual parameter, it may include something else for which we can understand this is the source of the sound is different, although they are producing the same fundamental frequency. Okay. So, that is the pitch in perceptual domain. So, main parameter, physical domain parameter of pitch is called fundamental frequency or F0. Many places I refer to F0 also, F0 fundamental frequency of that sound. Then loudness, intensity, physical parameter is intensity. I can measure the intensity 5 dB, 6 dB, 7 dB, but loudness is a perceptual parameter. I can say this is louder sound compared to previous sound, this is louder sound compared to previous sound. So, loudness is a perceptual parameter, intensity is a physical parameter. Timbre or sound quality. If you see, I can give an example, same musical grammar, same lyrics is generated from a two female speaker. Let us Lata Mangeshkar use the same lyrics, same musical note position and his so his song, the Lata Mangeshkar sing a song, recorded song. Same lyrics, same musical grammar is followed by some other singer also. Let us, he does not make any mistake and also produce the same song, but we can able to distinguish this song. I say if we perceive it, we say this song is better than this. Why? Because if I control this thing, then I can say the movement of the speech, the singing grammar is same. He also followed the same note, same position, same duration also. Then why this speaker, this is better than this? Because of the timbre, complexity of the speech. If this complexity I may like much more compared to this speech complexity. So, the production mechanism, that complexity, or you can say physical dimension is called spectral structures. We say it is spectral structures. So, or timbre or complexity of the speech is in perceptual dimension. I can say okay, this complexity, but if I say how do you measure it, one of the procedure is spectral envelope, spectral composition of this segment and this segment will be different. Okay. So, pitch, loudness, timbre, perceptual dimension, fundamental frequency, intensity and spectrum envelope is the properties of physical dimension of the sound. Okay. Similarly, you can see that there is a hue, brightness and sharpness, not shape, sharpness and then wavelength, luminance, contrast, all kind of things are there in perceptual dimension also. How human being is perceive a picture, that is called visual perception of a human being. Okay. So, we have again limitation in human perception of visual dimension also. So, speech dimension I have a limitation. So, I have to find out that limitation and you can say the visual dimension there is a limitation. So, there is an experiment to find out those limitations. Okay. Now, I am not describing this thing again. Now, human range of hearing, sound frequency and sound direction, both sound frequency and sound direction, threshold of hearing. So, there is a human threshold of hearing. So, threshold of hearing, that means the minimum pressure, acoustical pressure which can create a sensation in our nervous system is called threshold of hearing. So, suppose I produce a 1 kilohertz acoustical signal of pressure P which just create the human sensation in the ears, the normal hearing person. The person must be normal hearing person, not defect. So, there is defect I will not discuss in here. So, for a normal hearing person, the required amount of pressure to create just a sensation in the human ear is called threshold of hearing. Okay. Now, if you remember, I said the perception, or you can say the intensity perception of a human being for different frequency is different because of the outer ear and middle ear frequency responsive. If I draw that. So, I can say the sensation created, the amount of pressure required to create a sensation for 1 kilohertz and create a sensation for 300 hertz signal, maybe it will be different. So, 300 hertz signal required more power to create the sensation, but 1 kilohertz signal required less power to create the sensation. So, if I am able to define the threshold of hearing, then for a particular, you are defining the threshold of hearing for measuring the intensity. I can say, let us define the frequency for which I can say threshold of hearing, we said it is 0 dB. So, 0 dB is called threshold of hearing decibel for that particular sound intensity which require to create the sensation for 1 kilohertz signal. So, I can say 1 kilohertz acoustical signal or 1 kilohertz monotone, the amount of intensity required to create the sensation in human ear is called 0 dB. So, once I say 0 dB, it is not defined for all frequencies. 0 dB means I take a 1 kilohertz acoustical signal or monotone signal and I want to find out the intensity I which just create a sensation in the human being, that I call 0 dB. So, that I is called 10 to the power minus 12 watt. I think 10 to the power minus 12 watt per meter square. Okay. So, this is threshold of hearing. So, that is defined by 0 dB. So, what is dB? What is dB? Sometimes we said it is dB. dB is called decibel. Decibel. So, 1 bell is equal to log of I by I reference, where I reference is related to the 10 to the power minus 12 watt per meter square, which is defined as a 0 dB. Okay. Decibel. So, deci means 1 by 10. So, decibel means 1 bell is equal to 10 log I by I reference decibel dB. Okay. dB, decibel. So, if the intensity of a sound is I, then I can say convert in dB is nothing but a 10 log I by I reference, where I reference is equal to 10 to the power minus 12 watt per meter square. So, sound intensity of a sound is a physical quantity that can be measured and quantified. Acoustic intensity I define as the average flow of energy through an unit area. Area per you can say the power per unit area or force per unit area is nothing but intensity. Power per unit area is nothing but intensity. Okay. So, watt per square meter I by I 0 is 10 to the power minus 12 1. Okay. Now, decibel. Similarly, if it is instead of I is equal to p square by 2 rho c, or if it is RMS, all kind of conversion I can say. Similarly, instead of I, if it is measured in pressure, then I can say 20 log P by P reference, where P reference for, if you see P reference for air is 20 micropascal, for water is 1 micropascal. Okay. So, P reference intensity in air is minus 2. So, this is also depends on the conduction, the intensity. I said the threshold of hearing is the amount of sound pressure required to create a sensation in human ear for a 1 kilohertz acoustic wave. Okay. So, I can if it is water, then the amount pressure medium is water. So, it required less amount of intensity. Okay. So, this I am not going details, this is acoustical part, then conversion of dB to percentage kind of things, there is some mathematics also you can say, then loudness curve. Okay. Now, if you remember the combined frequency response of the outer air and middle air, I can say this is look like this. So, this way is the frequency, this way is the loudness in dB. Okay. Reference is 10 to the power minus 12 watt, 0 dB. Now, if you see for this frequency and for this frequency, this is for 1 kilohertz. Okay, this is 5 kilohertz, this is 200 hertz. Now, intensity required to create a sensation for a 200 hertz signal will be require high amplitude. Intensity created for 300 hertz signal required high amplitude, for 1 kilohertz this amplitude, 5 kilohertz this amplitude. So, this is called threshold of hearing curve for different frequency. So, this is the minimum intensity required to create a sensation in human ear. Since the frequency response for different frequency, the intensity frequency response of the intensity for different frequency, the intensity of the sound perception is different. That is why I said for 200 hertz I require larger intensity sound to create the threshold of hearing compared to 1 kilohertz. Similarly, I can say this is a 10 dB curve. Okay. So, let us 10 dB at 1 kilohertz. To perceive the same loudness for 200 hertz signal, I require larger intensity. To perceive the 300 hertz signal, I require larger intensity, but along this line the loudness which I perceive will be the same. You want to know 1 kilohertz 10 dB, maybe 300 hertz, maybe 20 dB I required intensity, but if I perceive that sound, loudness of the sound will be the same. So, I can say if I go along this line, the loudness will be same, that is why it is called equal loudness curve or phone curve, equal loudness curve or phone curve. So, along the line loudness will be equal, let us say it is 20 dB curve. Okay. So, perception of sound, this is the perception of sound, intensity is different. Intensity for 1 kilohertz it is 10 dB, maybe here intensity is 25 dB, but perception of the sound is same. That is why it is called, this line is called equal loudness curve. So, loudness is a perceptual quantity that is related to the physical property level or pressure level of sound or intensity, but it is not direct intensity. Okay. So, this curve is called phone curve or equal loudness curve. Now, how do you then measure loudness in sound? Sometimes it is called also sound. Okay. Now, I want to find out the relations between the intensity and loudness. How do you do it? So, I can say I design a perceptual experiment for I take a normal hearing capability sound, okay, and this axis I put normal human capability of hearing, normal hearing capability human being I take. Okay. I produce loudness in phone. So, I take let us 1 kilohertz acoustical signal, okay. 1 kilohertz acoustical signal I take, or equal loudness curve, if I then composition we have to take. So, let us 1 kilohertz signal. Then I produce, take the let us intensity A dB, and I produce the sound, listeners perceive it. Then again I produce the take A1 dB, listeners perceive it. I told the listeners, when you perceive the sound is twice than this A dB, you raise your hand. So, I first produce let us A dB sound to the listeners, I told him, and next A1 dB, and gradually I increasing the dB. I told the listener, when you perceive the loudness is double, then you raise your hand. Then I can say the here he perceive the loudness is double, here he perceive the loudness is double, here he perceive the loudness is double. Then I can draw that curve. Then I derive the equation of the curve and find out the loudness scale and relation between the this is intensity and this is the loudness. So, loudness and intensity relation, this is the derivation of the loudness and intensity relation. I am not deriving it again. So, L is equal to 445 I to the power 0.333. So, that can say if I know the intensity, equal loudness in SON. So, this will be SON, SONES, that much of SONs. So, L is equal to 445 I to the power 0.33. So, if it is 5 dB, if I know the intensity, then I can calculate loudness. Okay. So, this is the loudness SON curve. Then there is a example, this is called sound pressure level for different, if it is 160 jet engine close up, threshold of pain 130. So, if you see this, we should not expose to the large amount of sound, large or high amplitude of sound. If it is high amplitude, it can create pain in our ear. Okay. So, threshold of pain is 20 to 130 dB. If I expose to a sound intensity of 130 dB, it can create a pain in the ears. And also if I expose more than that, then my ear permanently can be damaged also. Okay. So, then if you see the pollution control board has said that do not produce the sound which is more than 60 dB. If it is more than 60 dB, it may cause hearing problem, or it is not good to expose in a always above 60 dB sound environment, then you may have some problem in your listening. Today, if you see, lot of people are wearing a headphone many times, let us that in 24 hours, 8 hours or 12 hours they wearing the headphone. What is the problem? What can affect? So, once you wearing a headphone, it lose sound localization is lost. That means, you wearing a headphone and walking in a road, you cannot distinguish whether the car is coming on your front or in your back. Forget about that, you just close your eyes, you cannot listen that horn also, and also car noise also, car sound also. So, if you wearing a headphone, sound localization happen inside your ear. Now, if you expose your ear with a continuous stimulus, so this is a 24-hour you are listening to music. So, you are exposed, your human ear is exposed to a continuous vibration that can damage the elasticity problem of your middle ear. So, the elasticity of your middle ear may be lost. Then what will happen? That maybe response curve will change. So, you may be your distinguishing sound listening capability. So, low intensity sound you may not able to listen, or you cannot hear the low intensity sound. So, your threshold of hearing will be increased, continuous exposure to the sound. So, that is why if you see the person who are working in a factory environment, his threshold of hearing is increased. So, he cannot the low intensity sound he cannot hear. So, your sensitivity of your ear is decreasing, that is the problem. So, do not expose your or do not you expose your ear continuously in a sound environment. Do not expose your ear to a very high intensity loudness or high loud sound, because that can permanently damage your ear. Okay. So, do not expose that things. So, there is a sound propagation, you know that even if a source is produced 120 dB, you may say I am, if it is 10 feet away, then you know the 1 by r square. So, I is reduced in 1 by r square form. So, if your distance is double, 6 every doubling the distance 6 dB down. So, if it is source away from the source 10 feet, it will reduce the sound intensity, but do not always expose in a large sound, so that your ear sensitivity is lost. Okay. So, there is threshold of hearing, threshold of pain, all are there. If you see this curve, sound intensity level, and this is the black line is threshold of hearing, this is the music and this is the speech region, loudness of the speech region. Okay. Contour of damage risks and threshold of pain is here. Okay. So, next class we will discuss about the frequency perception. Okay. Thank you.